Slide text. How containers work under the hood.
Should be good to go.
Text. Elizabeth Trenta.
Awesome. Well, welcome everyone. Uh, This is How Containers Work Under the Hood by Nuwan Kumarasiri. Nuwan is the engineering manager for enterprise integration, leading the registrar's office, application development, or the road team. He's a full stack software developer with experience implementing various data intensive and end consumer facing applications for various domains such as higher ed, retail, health insurance, and others. In his spare time, Nuwan works on document producing software and tools. If you have any questions for Nuwan over the course of this presentation, please feel free to put them in the chat to go through at the end of our session today. But without further ado, how containers work under the hood.
Nuwan appears.
Okay, thanks for that intro, Elizabeth. My name is Nuwan Kumarasiri. I'm with Division of Information Technology, Do It. I am leading a team of software developers that maintains a few student-facing application for the registrar office. You may have heard about COSICH and Enroll application, UW-Madison degree audit application, and then UW-Madison residency application. So those are some of the application that my team is maintaining. We heavily rely on Amazon Web Services, AWS, for hosting these applications. And then we use containers as a way to deploy these applications inside AWS. So that experience led me to look into a little bit more detail how containers work, and this is that summary. And hopefully you'll be able to gain some insight how containers work under the hood, and also maybe learn a little bit more about some of the tools that's available to debug in these some of these containers in various environments.
4 container logos lie in a line.
All right. So what's a container? So the container is basically you can think of as a box, a way to separate from things from each other. So container is a way to isolate set of system resources, right? Let's say CPU, then your memory, then the disk, that sort of system resources. To isolate those system resources at process level. So let's say you have like multiple programs running in your system, and you want to build some sort of like isolation among them. So container is a way to go about doing that. So you may have heard there are so many different container technologies out there. One of the very famous ones is being a Docker. So then there is Firecracker. It's another container technology. It's developed by AWS, Amazon Web Services. If you're using things like Amazon Lambdas, Amazon ECS services, so those type of containers are deployed inside what's called the Firecracker. And then there's another container technology called Kata, or really small containers. And also, if you're familiar with Kubernetes, there's something called Kubernetes pods that, again, like really small containers that you can deploy into these environments. So all these different container technologies under the hood, they use the same Linux technology that we will look into. So what are the benefits of containers? There are like two benefits, right? For the first thing is sandboxing. It will give you an environment where things will be isolated to a particular set of resources. Let's say you are like a cybersecurity researcher, or you are a malware researcher, and if you want like some sort of environment that you want to experiment with things, experiment with malicious file without that impacting other part of the system, other part of your computer. So that's a really good use case for containers. So basically sandboxing. Or let's say you are a developer, you compile your software, you build an artifact from that, and you need to make sure that that same artifact will work in a user's environment. And in order to verify that, you can try to build this software or the binary within a container. And there are like a lot of really good tools that you can build out of this sandboxing environment. For example, if you want to build like a system that build your application in a predictable and repetitive manner, those type of tools can be built using these containers or sandboxing. So the other benefit is resource control. Let's say you want to put some limits into this system should only utilize this much of the CPU, or this system should only utilize this much of memory. In a situation like that, you can again use containers for that, to provide better quality of service, maybe provide better SLAs. Let's say you have like a high demanding customer in a shared environment, shared web hosting environment, where you want to provide really high quality service to one customer with a lot of resources. Then you can allocate a lot of resources to that customer. And then on the other hand, there's the second customer, they don't have a lot of usage, so you want to allocate less resources for that customer. So in an environment like that, you can again build a resource control and then build various SLAs, quality of service using containers. So these are some of the applications and benefits of using containers.
3 info boxes.
All right, so how containers are built. So we are just going to look into the underlying technology. So we are going to focus on Linux here. Most of these container technologies are built using Linux. So other operating system, they provide containers technology, but we are going to primarily focus on Linux. So Linux operating systems implement containers using two technologies. One is called namespaces, other one is called C groups. C group stands for control groups. So namespace is a abstract where you can isolate a set of resources so that it appears a program or a process that utilize that set of resources belong to that process alone. If you're familiar with like packages, a module, it's the same concept. So we give some sort of abstraction, isolation, so that other part of the system, other programs will not see what that namespace is. So basically, we're providing isolation. So the control groups, that's a way to provide control to a set of resources. It's a way to organize set of programs into a hierarchical group, so that the resource usage, memory, CPU, disk I/O, network I/O, that sort of things can be limited and monitored. So these are the two technologies that Linux uses to implement containers.
The processes flowchart has blue and yellow boxes.
So this diagram highlight a little bit more about what namespaces are. So for example, in any system, you have like multiple programs, generally known as processes, working with each other, right? You might have like a word processor, your Microsoft Word document that you write some document, you might be listening to some music, you might be downloading a large file from the internet. So these programs use shared resources with each other, right? We have a CPU, we have the memory, we have the disk, we have then the network. If you download a large file from the internet. So all these programs, your word processor, your music player, your web browser, these will share these resources. With namespaces, it will give each of these programs, processes, an abstraction of those resources, so that they see all those resources belongs to themselves only. And so that's the idea behind namespaces.
The table lists namespaces.
All right. There are 7 namespaces in Linux. First one is UTS, what's known as Unix time sharing namespace. So every computer, every system has a host name. So with UTS namespace, that allows a container to have its own host name. So if you're familiar with Docker, you might know, like, when we start a container, you can assign its own domain name or the host name. If you have like 2 containers running on the same system, you can assign 2 host names. So that's done by what's called the UTS namespace. Similar to that, there's another one called network namespace, net for short. So that's basically isolate all the network related resources, your network card, your IP address, your routing table, things are related to networking. So those that's done by what's called the network namespace. So there's another one called times namespace. So that allows these containers or these different processes to have their own view of system clock. Again, if you run 2 different containers, and if they want to have 2 different view of 2 different system clocks, one is running, let's say, CDT, another is running PST. So you can do that, right? So that's done by what's called the time namespace. So similar to that, there's another namespace called mount. So that's basically associated with your file system. Again, that allows a process or a container to see a list of mount points, isolate to that process alone. Similar to that, another one is process PID namespace. That allows the process to see the set of process ID isolated to that process alone. Similar to that, there's another one called user namespace. So in any Linux system, the permissions are managed by users and then groups. So with user namespace, that allows each container or each process to have its set of own isolated set of users and group. In a Docker container, if you run like 2 containers, you can basically see what are the users for. You can assign users and group ID for the container 1. Similar to that, you can assign users and groups for the container 2. So that's done by user namespace. So there was also another namespace called IPC. It's the interprocess communication resources. So those are the namespaces that in Linux that's being used in container technology.
Flowchart.
All right. So how do we use these namespaces to implement containers? So in Linux, if you want to get something done, the interface is what's called the system calls. It's basically, let's say we want to like download a file, right? We want to play a music. If you want to do those things, and the program will invoke what's called a system call to the operating system, and then it will basically invoke the respective hardware to get that work done. So similar to that, namespace can be used using system calls. There are like 4 system calls that's related to namespaces. The first one is clone.
System call list.
Clone is basically a system call that allows us to create a copy of a running program. Clone is not directly related to containers, but it's the way to create another copy of the program. So the interesting thing here is that we can pass argument into clone, like basically when we initiate a new process, new program, we can pass argument to indicate I want this process or the program to be associated with this given set of namespaces. So that's the way we say, okay, this program, this process is belong to this container. So there's another system called pivot root. A pivot root, what mean it's basically pivoting the root, pivot root. So basically change the root mount point when we call the when we try to like clone the process and try to attach a namespace to that. So basically, it allows us the ability to change the root file system. I have a diagram why that's important. I will get into that in the next slide. So the next system call is unshare. So allows part of the process or the program to deassociate it with the namespace. If a process is using a multiple namespaces, so a namespace, it allows you to deassociate it with those, deassociate from those namespaces. The other one is set namespace. That's the opposite. So it allows to a running program or a process to associate with the namespace or multiple of those. So these are the 4 system calls that we use to create containers. So if you consider any of those container technology, Docker, Kata, then Firecracker, or the AWS containers, or Kubernetes pods. So this basically they all use these 4 system calls to create these containers.
The next slide has 2 large flowcharts.
All right. So let me talk a little bit about pivot root, the importance of that. So as I mentioned, pivot root is basically pivoting the root. So let's say this is a normal hierarchy, like a file system in Linux. So you have your root folder, you have your home folder. Under the home folder, you have your users, and under users, you have your various directories. So what pivot root does is it allows us to change a directory from one root to another. So in this example, let's say I want to move user 1 from /home to, I have this temporary folder called rootfs and inside /temp. If I want to move user 1 from /home to rootfs, I can do that using pivot root. So this is how it's done. So we basically say pivot root from /home to rootfs, and then mark rootfs as the new root. So what does this do? So as you can see in the diagram on the right-hand side, user 1 has a new root now. So it gives the idea that user 1's root is basically this folder that's available under /temp. Now, if you put some of your other programs inside the new root, like let's say ls, which basically use for listing programs, or listing content in the directory. So you can place that program inside that new root so that will be available for user 1. Or you can place your own programs. Let's say you write a program to do something, and if you place that under that new root, it will be available for user 1. So this is how we build Docker images. Basically, it's an archive with the new file system, with all the programs that we want, and we provide an archive so that we can run it using those 4 system calls that I mentioned earlier. So yeah, so this is how containers work. This is how we build images, archive, and then we execute those containers.
The next slide lists code lines.
All right, so the next one is the C groups. So those 4 system calls, we use those to create containers, and we use C groups for resource controls, auditing, and monitoring. So basically, C group is a way to arrange resources into hierarchical groups using text files. So how we do that is we basically place different type of C group types configuration files inside /sysfs C group file system. So here's an example. So I am going to create a C group for managing memory, restricting access to the memory called foo. And I'm going to create a directory called make dir minus p inside that memory C group folder called foo. And then I'm going to limit the memory to 256 megabytes using that memory.limit in bytes file. And then in the third command, I'm going to attach a process or a program to that that C group. So what it does is basically it's saying limit the amount of memory for this process just to 256 megabyte. So just like memory, there are other resources, right? You can configure the CPU, put the limits on the CPU. You can put limits on the disk. You can put the limit on network. All these resources you can configure using this text file inside sysfsc group folder. So that's why it's hierarchical, and we configure C groups using text files. So if you have used Docker, again, you may have run a command like this just to limit the allocated memory for the Docker container. And if you do something like this, so that's what it does under hood. It basically create all these configuration files inside sysfs and utilize C groups to control the resource usage.
The table lists 4 commands.
All right, so that's how basically containers work. All these technologies, they use all those two things, right? Namespaces and then C groups. Namespaces are configured using for system calls, and then C groups are configured using text configuration files that we place in a hierarchical manner using sysfs file system. Yeah, so all those technologies that I mentioned, they basically use those two things. Okay, here are some tools, commands that you can use to debug some of these containers and in the namespaces. By the way, if you manage some of these environments, you might not need to, I guess, rely on some of these tools available in Linux, because most of these container management system, they have really nice dashboard visuals and other tools that allow you to monitor systems. But on the other hand, it's good to know about some of these tools available in Linux by default. So the first one is LSNS, that allows us to list the namespace. You can say, for this program, what are the namespaces that it's owning? So in Docker word, you may have issue a command like docker ps-a. So that's the very same thing it's doing. Then the proc file system. You may know in Linux, proc file system provide a lot of really valuable information on how Linux kernel works internally. So with namespaces as well, you can rely on proc file system to see what are the namespaces, which process is using which namespaces, things to identify things like that. So inside proc file system, there will be a folder for your process or the program, and then there will be a folder called namespace ns. Inside that, you'll find different type of namespaces for your CPU, for your memory, so for your time, things that we discussed. Again, a lot of really good information that you can collect out of the proc file system. The other command is ns-enter, so that allows you to go and log into a namespace, so that again you can inspect that namespace. You may have used the command like when you have like a Docker container running, if you really want to go and log into the container itself, you may have used Docker exec. So that's the same thing that it's doing. Basically, it's doing a something very similar to ns enter. Then IP command also you can use netns. So basically, IP is the command to look for all of your internet networking resources, your network card, your IP address, your routing information, things like that. So it has an option to use display the network namespace. So there's that. Finally, PS command that you can use to understand more about your process. It also has an option to pass C group. So that way, like, you can identify all the C group that the process belong to, and then figure out all these details from for a process. You may know, like, PS command rely on the data available inside proc file system. So it's basically another really nice representation of the data that's already available in the proc file system.
The reference slide comes next.
All right. Yeah. So these are some references. So there's this. I wrote a small program called container using Go programming language and also C programming language to demonstrate how to use those 4 systems calls that we discussed, how to put them together to build a really tiny mini version of let's say Go container, right? So you can go and take a look, and these are the documents for all those system calls and tools that I mentioned. They have a ton of really valuable information that you can refer to. Yeah. So yeah, in summary, all these containers, Linux containers, are implemented using 2 technologies, namespaces, and then C groups. I think that's all I have. If you have any question, I'm happy to answer. Otherwise, thanks for listening.
References on the slide are written in blue link text.
Thank you so much, Nolan, for that presentation. If there are any questions, you can feel free to put them in the chat, or you can also unmute and ask. We have a couple minutes left until we wrap up. Again, thank you, Nolan. That'll be applause in chat.
No problem.
Slide text. References. Container.go. Container. A container implementation in Go and C languages. System calls. Namespace 7. C group 7. Clone 2. Pivot _ root 2. Unshared 2. setns 2. Tools for debugging. LSNS 8. NSEnter 8.
Okay, yeah, there's a question. What does your team do it mostly use? Yeah, we use Docker containers. Would you have good?
What made you choose Docker versus the other options?
So we heavily rely on AWS services, and they have like a really good support for Docker containers. So if you build a Docker container, you can deploy that inside the ECS and also as a Lambda container. So we can basically reuse the same thing. So I think that was the reason.
Gotcha.
Yeah.
Very straightforward. Thank you.
Would you have good reference to the materials based on your yeah? So I think if you go through the reference, they have like really good set of information on those manual pages, and also you have my email address. You can email me for any questions, and there are a ton of references on the internet. Oh, here's another great question. Are there any similarities between virtual machines and containers? So I would say containers, as we saw, like they are like inbuilt into the operating system, like kernel itself. We basically use 4 system calls. So those are those are because of that reason, those are like really lightweight. On the other hand, VM, those are like really heavyweight. There's a entirely separate programs that runs on top of the Linux or any other operating system to virtualize all those resources, like let's say your disk, your memory, your display, your I/O, things like that. So a lot of heavy lifting is done inside VMs. On the other hand, containers are very lightweight, not very resource consuming. Yep. All right. Yeah, thanks for all the questions.
Yeah, we've reached the end of our session. Thank you again, Nuwan, for this awesome presentation. We are going into our lunch break now, so we will be back at 12:20 with 4 more virtual sessions. Thank you again for attending. If you have any more questions, Nuwan's email is in chat. You're welcome to stay on for as long as you'd like, but otherwise we will see you in the afternoon.
Wisconsin flower background.
Thank you.